Good morning. Happy Wednesday. Feels like a Monday, kind of, but it's a Wednesday, whatever. I hope you had a great Veterans Day and your week has been going well so far. Section 01 and Section H1, the next thing you're going to do for me will be the same, but it's on different days. So, of course, Section 01, those of you with Monday Lab, what I'm going to say applies for next week, Monday, at 1:10 p.m. But we have a lot of people here from H1, which is awesome, too. That'll apply for today. So the next time I see you at 1:10 p.m. and 25:01, what you'll do is you'll turn in the Exam Prep 2 worksheet, a series of 5 questions, show your answer kind of stuff, should be cool. The unknown chloride lab that we did last week, and we'll take the second midterm exam, which is the focus of the study session. The exam will be about 2 hours in length. Bring your calculator. Page of notes is cool. You'll staple it to the back when you turn it in. A periodic table I've got, or you can have your own stuff is fine. We will go next door afterwards and do the calorimetry lab. The calorimetry lab is one where you'll need some goggles, so if you have them, bring them. If you don't, I got some you can borrow. The exam itself has 20 multiple choice questions and 4 short answer questions, so similar format to exam 1. It'll go the whole 2 hours. We're not going to talk about problem sets or anything like that. And then the next time I see you, I'll return the midterm to you with a summary sheet. And the summary sheet at the end will say how you're doing in the classes at this time, stuff like that. Cool. I'm going to do as much of the review here as I can, but I do want to let you know that the whole review is available as a YouTube video. If you go to mhchem.org/w/h.htm, you can see all of the problems. If I rush through them, you can then go back and hear a little bit more relaxed version of me explaining to it. Any questions? Stuff like that. All right, let's do this. These first 2 questions, you're welcome to participate if you want, but I'm just going to buzz through them. These are questions that really talk about net ionic reactions. So this first reaction is a reaction between magnesium carbonate and nitric acid. So magnesium carbonate has a carbonate, CO3 minus 2, with magnesium, group 2A is positive 2, so MgCO3. And HNO3 is nitric acid. The magnesium and the hydrogen swap places, so magnesium starts dancing with nitrate. If it's positive 2 on this side, it's positive 2 on the other side. Nitrate's always -1, so you'll need 2 of them, so it makes magnesium nitrate. And H plus and CO3 minus 2 make what looks like initially H2CO3. That's the unstable acid that breaks down to CO2 and water. So this reaction right here is the balanced molecular reaction. If you take out the spectator ions, which are things that aren't involved with gases, liquids, and solids, what you want to do is you want to look at pieces that are AQ on both sides, and nitrate is on both sides. So if you pull the nitrate out, you get answer B. This is answer A without the nitrates. So nitrate would be the spectator ion, MgCO3 solid stay, CO2 gas, and water liquid stay, and you have just the remaining ions left over. This is a gas-forming reaction. CO2 and water are made. There's also acid-base reactions, precipitation reactions. Any questions on that? Okay, this question is very similar. This is a question where we have potassium hydroxide, KOH, and iron 2 chloride. So iron 2 means you have an Fe+2 ion, and chloride is Cl-. So FeCl2 is iron 2 chloride, potassium hydroxide is KOH. And on the other side, you have iron 2 hydroxide and KCl. Now this one, it doesn't really state much about the types of, if they're solid, liquid, or aqueous. Anything with K+, and almost all the time things with Cl- are usually AQ. So that includes this one because it's got a K. It includes this one. Remember, chloride is only insoluble with silver, mercury, and lead. Iron is not that. So that's going to be AQ, that's going to be AQ. And most of the time, the negative polyatomic ions like hydroxide, they usually are insoluble. So hydroxide with anything that's not Na+, K+, or Li+, will usually be a solid. So this is the balanced reaction right here. If you take out the ions that are common to everything aqueous, I think you get answer C. Yeah. So the K+ and the Cl- in this reaction are both spectators. This is a precipitation reaction because a solid is being made. Stuff like that. Any questions on that? Okay, I do want to spend a little time with this one though. This is a redox reaction, and I'm asking you here to find out which of those is a correct statement. And so in this one, I'd like you to figure out what's being oxidized, what's the reducing agent, etc., etc. Remember that the agents are the opposite. So if something is the reducing agent, it means that it's oxidized. And if it's the oxidizing agent, it means it's reduced. See what you can figure out. So on a question like this, you should first figure out if it's a redox reaction or not. And there's a couple different ways to do this. But one way is you can literally look at the atoms on the left and the right side. And remember, redox is all about losing electrons or gaining electrons. So if you look at just zinc going to zinc 2 plus, all right, is zinc losing or gaining electrons? Losing, that's right. So because zinc is doing something, it is a redox reaction. We may not know what's doing what quite yet, but answer E is off the table. So literally, seeing that zinc goes to zinc 2 plus, that means that some electrons are moving around, so it's going to be happening. And what a lot of you said, which is awesome, zinc going to zinc 2 plus, zinc has lost electrons to become zinc 2 plus. So lose electrons means that zinc has been oxidized. We now know that it's going to be either answer A or answer C. It's not going to be B. If it was reduced, like zinc would go to zinc 2 minus or something like that, it would gain electrons. And that has not happened. Zinc has become more positive. That can only happen if it loses electrons. Now, the easiest way to go from here is if you remember that reducing agent is the opposite. It's not being reduced, it means that it's being oxidized. And in a redox reaction, something has to lose electrons, but then something gains those electrons back. You have to have something both oxidized and reduced. And what this statement is saying is that something is oxidized and a reducing agent, something is oxidized. That doesn't sound right, all right? That sounds weird. So by default, I would say answer C. Something weird is going on with the vanadium here. It's hard to say at this point. I would guess answer C. Now, guessing I know is dangerous, but anyway, if you want to really nail this down, you can use oxidation numbers. Now, zinc, like all the elements, are 0, and all of the ions, that is their oxidation number. So zinc has become more positive. So that's what happens when something loses electrons. The reduced piece will become more negative. That's right. So here, this is a little weird, but you have two -2 oxygens, -4, and an overall charge of +1. So we don't know vanadium, X, but we have two -2 oxygens, and all of that equals the charge, if any, on the ion. So when you find what the vanadium is here, you put -4 on the other side, it becomes +4. This is a +5 vanadium. It's a vanadium +5 ion. And if you do it down here, well, we don't know this vanadium either, but oxygen's almost always -2, and the overall charge on this thing is +2. So X plus -2 equals +2, add 2 to both sides. This is a +4. So vanadium has went from a +5 to a +4. It's becoming more negative, and that can only happen if you have negative electrons. So for all of these reasons, answer C is the right way. First, you just have to identify if it's redox or not. All right, zinc going to zinc 2+, bam, this is redox. Zinc has lost electrons. Losing electrons means oxidized, and in this problem, you just need to figure out what is being reduced. It has to be an oxidizing agent of this thing. You could prove it here. It really is like +5 to +4. Questions? Now, all of the reactions we did in the net ionics lab, all those double displacement reactions, none of them are redox. So the last two examples I showed you with the iron and the magnesium, neither of those are redox, and that's a big hint for you. So if I ask you a question, which of these reactions is redox, and you see a precipitation reaction, not redox. Okay. Now, this is a question with molarity, moles per liter. Every time you see that big M, think moles per liter. And what I'm trying to get you to do here is find the concentration or molarity of the sodium carbonate. How many milliliters in a liter? 1,000, good, that's right. That will be important for the midterm to know. 1,000 milliliters per liter. See if you can figure out which of these answers would be the best concentration of the sodium carbonate. Okay. So if you see concentration, or if you see the big M, they both mean molarity, moles per liter. And you want to have moles in the top and liters in the bottom. So in this problem, you have 6.73 grams of sodium carbonate placed in 250 milliliters of solution. So you want to turn grams into moles. The molar mass is what you need to answer that, which I gave you in the problem. So 6.73 divided by 106 will give you the moles of sodium carbonate. And then you turn 250 milliliters into liters. So remember 1,000 milliliters per liter. So this divided by 1,000 is 0.250. If you got 0.254 molar, big M, good to go. Any questions on that? Cool. It's always moles per liter. And in this problem, you can use the grams to turn it into moles for the numerator, divided by the liters of solution. Cool. Okay. A lot of times, solutions are diluted to make them less concentrated. And so in this problem, we have 0.25 molar hydrochloric acid and 60 milliliters of it. And we're placing this amount of HCl in a 500 milliliter volumetric flask. And the question is, what's the new concentration of HCl? So if you see one of these concentration diluted kind of problems, you can go M1 V1 equals M2 V2. I like that one because you can keep the volume in milliliters, but you can also do this a couple different ways. See if you can figure out which of those answers would be the correct concentration. All right, your answer, M2, will be a number smaller than the concentration you started with, so smaller than 0.25. You're adding water, and water makes the strength, if you will, of the solution get smaller. So on this problem, 60 milliliters and 0.25 moles per liter go together. So that's a V1, and that's like an M1. And then this number is the V2, the new volume, and you want to find the new concentration, M2. So up here, you can see how I kind of set it up for M2. M2 is going to be 0.25 times 60 divided by 500, and I got 0.030 moles per liter. And again, check yourself. The new value should be smaller than the initial molarity. You are welcome to use milliliters on this because it's like V1 over V2. There's nothing wrong with using liters, but lazy chemists of the world, milliliters work really good. Any questions? Okay. pH is really handy for chemists to figure out quickly if an acid, or excuse me, if a solution is acidic or basic. And here we have a question that has a concentration of nitric acid, 0.030. I'm just going to show you the answer on this one. I'm hoping this is pretty chill, but you want to go pH equals minus log H3O plus. This is the base 10 log, so log is what works really well on this one. So literally in your calculator, minus log, this number right here, you should get 1.52. Now, if you don't have the ln button on your calculator, or the log button on your calculator, you probably have the ln, the natural log. And what you can do to make this work is minus natural log of the hydronium ion concentration divided by natural log of 10 in the math world is equal to minus log of the H3O plus. So if you have log, that's easy, just minus log 0.030. If you don't have that button, you can do this natural log thing right here. If it gives you a molarity for this part, it's going to go right in that part right there. All of the nitric acid goes to this hydronium. That's why it's the same kind of number. Questions? Cool. This question, we'll slow it down a little bit again. This is a question where you have so much nitric acid, HNO3, and you want to find out how much sodium carbonate it takes to react with it. So imagine you want to get rid of it. It's been sitting in your basement for a while. What you want to do, turn this number to liters. Liters times moles per liter will give you moles of nitric acid. And then 2 moles of nitric acid need 1 mole of sodium carbonate. And once you have that number, you can multiply by the molar mass of sodium carbonate to get one of these answers right here. So see if you can do this kind of stuff. This is volume to moles to grams kind of a problem. The balanced reaction says that 2 moles of nitric acid are needed for every 1 mole of sodium carbonate. So your first part is just to figure out how many moles of nitric acid you've got. So 25 divided by 1,000 is 0.025 liters, 0.0250 liters. Liters times big M, moles per liter. The liters cancel out. We've got moles of nitric acid. Then 2 moles of that require 1 mole of sodium carbonate. So that allows you to figure out how many moles of sodium carbonate you need based on the nitric acid you have. And then finally, you can measure out the grams by using the molar mass of sodium carbonate, 106 grams per mole. So up here on the board, I turned milliliters to liters. I multiplied by molarity, which again is moles per liter, and the liters canceled out. Then there's 2 moles of nitric acid for every 1 mole of sodium carbonate. That's from this part of the balanced reaction. And then you multiply by the molar mass of sodium carbonate to get the grams. And if you do all of this, 0.205 grams is what you should get. If you forgot to go milliliters to liters, it comes out to be 205 grams, stuff like that. If you do this problem, you got this section. Any questions? Okay, we're now going to change gears and talk about the calorimetry and thermal stuff. This is the heat transfer. And in this problem, you have a piece of copper. It's being heated for a little bit, and 100 joules of energy are transferred to the copper. The copper goes from 20 degrees to 71.9 degrees. You can use all this information to find the heat capacity. Now, Q equals mc delta T is the equation you want to use. C is the heat capacity. So see if you can solve for C based on this information. You don't have to turn grams into moles. Spoiler alert, 2 seconds, it doesn't do anything here. See if you can use the rest of that though to figure out which of those answers make sense. Okay, so Q equals MC delta T is like the first big equation. And if you see Q or delta H, those will always be the joules, kilojoules, these kind of things. Joules and kilojoules are a measurement of energy. When they're positive, like here, energy is being absorbed by the system, negative, energy is released. Don't have to worry about that right now. So Q equals MC delta T. Q is 100 joules, all right? And M is usually grams in these problems. So in this problem it is, so 5.00 grams is the M value. And you want to solve for C, that's the heat capacity. And then the delta T part, delta is always final minus initial. So because this is a temperature, it's final temperature minus initial temperature. And the really cool thing about delta T is you can use Celsius or Kelvin and you'll get the same delta T. We talked about in class, like 100 Celsius to 0 Celsius is the same as 373 Kelvin to 273 Kelvin. So you can mix and match, which is really kind. So even though these say Kelvin up here on the board, I just use Celsius because delta T will be the same in Kelvin as it is in Celsius. So you basically just want to solve for C. C is going to be this Q divided by 5. You divide it by the delta T value. And if you got 0.385, pat yourself on the back. Now, these heat capacity values, it means as you add heat, something gets hotter. And that happens all the time. So C values will never be negative because a negative C value would be like you give heat to something and it gets colder. And that's kind of cool on a science fiction level, but it doesn't happen in the real world. So answer E is not even possible as far as science knows. Metals usually have heat capacities under 1 joule per gram Kelvin, all right? So of these values right here, metals usually would be A or B. The values larger than 1, like water, which is 4.184, those would usually be for covalent bonded things with non-metals and non-metals in them. So these are just some hints and stuff to kind of help out here a little bit. Yes?
If you do get a negative value, would it be like the absolute value of that, or did you just do it wrong?
Yeah, no, and that was the other thing I was going to say, so very, very cool. If you do get like a negative right there, I would have high confidence that you can just absolute value and turn it into a positive. It usually means, Manuel, that the delta T was flipped, all right? And that's legit too and stuff. So more often than not, 99% of the time, absolute value it, and you're good to go. Good call. Other questions? Okay. This question, we have 2 different samples of water. All right. And in this one, 108 grams of water at 22.5 are mixed with 65.1 grams of water at an unknown temperature. And if everything is said and done, the final temperature of everything is 47.9. And the question is, what's the initial temperature of the water? Now, first of all, before we even start this problem, it's very helpful to think about what is cold, what is hot, and what is warm, all right? And warm is the temperature that everything ends up at, 47.9. Now, we know that this is the temperature of the initial stuff. That's a colder temperature. So this value, this is going to be the cold part right here. So whatever temperature you calculate, it should be a hot temperature. It'll be a number larger than 47.9. So answer A would be silly in this case. But see if you can do this. We're going to do an MC delta T hot plus MC delta T cold equals 0 on this problem. I'll start working on it here and you can start working on it too. Okay, so on a problem like this, thermodynamics, the first law says that you don't create or destroy any energy. And so what you can do then is set Q cold plus Q hot equals to 0. That says that the cold part plus the hot part, when they come together, they're sharing their energy to become a warm value, but they're not going to create or destroy anything. So if you do that, there's going to be an MC delta T for the cold water. So 108 grams of the cold water, 4.184 is the heat capacity. Delta T will be the final temperature minus the initial temperature. So all of that is just going to be a number. And you add that to MC delta T for the hot. Now you know that there's 65.1 grams of it, 4.184 is the heat capacity. Delta T, the final temperature, is 47.9, but you don't know the initial one. So one way to do this problem would be to solve it that way. And you can solve for x. You're going to have a number here, you're going to have another number here, and a number minus x. Solve for x. You'll get to it. If you got answer D, that's awesome. Now, you can also do it Q hot equals minus Q cold, or Q cold equals minus Q hot, whatever. You can let a minus sign be on the other one of them. The advantage of this way, you don't really need the 4.184. It cancels out. I still want you to know it, all right, because we'll use it once in a while, but that's an alternate way to do it. And if you do that, which I went through the steps here, it comes out again to be 90. So just remember that hot plus cold equals warm. Warm would be the final temperature, 47.9. So the cold went up to 47.9 to make that happen. And then the hot water, which we don't know what its initial temperature was, but the hot water then went down to 47.9. And what this tells you is that the initial water was 90 degrees Celsius. Any questions? Now, questions like this might seem daunting at first. You have a molar enthalpy of combustion, which is a lot of words, minus 20.44 kilojoules. Now, what that number means is that when you do this reaction, like 1 mole of this, you're going to get minus 2,044 kilojoules of energy out. But if you would multiply that amount by 3, i.e. if you had 3 moles of propane, you would take that number and multiply it by 3 to see the total amount. So 1 amount of propane gives you this much. 3 times that would give you 3 times that number, which is 6132. Notice this is a negative sign. Negative means exothermic, energy is being released. And propane, which is used in a lot of barbecues and stuff like that, propane definitely gives off a lot of energy. So these numbers are per mole, usually of propane in this case. The exciting part, if you had 3 moles of it, you would just multiply by 3 to see what was going on. Questions on that? Okay. This is a problem where you want to have delta H products minus delta H reactants. And I'm giving you the values there for the different products and reactants. See if you can figure out what the enthalpy of this reaction will be. Again, it's delta H products minus delta H reactants. See if you can figure that out. I'm running out of time here, so I apologize, but delta H products would be these two minus delta H reactants, those two. So SiO2, this number, plus 2, which you're going to multiply these by 2 times this number, that would be delta H products. And you subtract the delta H for this thing, there's no oxygen, but all the elements in their standard states are 0. So usually if you don't have a value, that means it's going to be 0 for what it's worth. If you plug this all into the math, it comes out to be minus 1428.8 kilojoules per mole, or kilojoules per reaction, really. So if you burn 1 mole of this, you'll get this much energy. If you burn 2 moles of this, you get twice this amount, stuff like that. Now, I want to show you a couple more problems. The full review, mhchem.org/w/h.htm, is a video where I go through all of these in a lot more detail, and I'm not rushed. So if you'd like, you could look at that. Or if you have a phone, take a picture, and you can look at the answer to see what's happening. This question was about heat of formation. If you see a delta HF, or a heat of formation, 1 mole of product, and all reactants are elements in their standard states. So answer B here follows that, only 1 mole of this, and all the reactants are elements. This one doesn't follow it because you have a compound, it's not an element in their standard states, stuff like that. So anytime you see delta HF, that's what you want to do. The last one here is an example of Hess's law. You want to find a delta HF for FeCl2. So to do that, you first need to figure out what the delta HF is equation. You'd have 1 mole of FeCl2, and the reactants would be elements in their standard states. In both of these reactions, there's an FeCl3, so you want to get rid of it. So you want to flip the one reaction around, change the sign. Then when you add them together, they all come out to be the reaction you're looking for, minus 341.8. Michelle.
I read that one.
mhchem.org/w/h.htm. I can email you a link to if it's hard. I know it's my handwriting is bad. So. Sorry, this is so fast, man. So, any questions? All right, I will see some of you today for lab. I'll see the rest of you on Friday. We're going to start chapter 6 stuff on Friday. Have a great day. Thanks for being here.